right, so I'm going to go ahead and tell you. Number one, this is a test question right here. What in the world does VSEPR mean? Valence, shell, electron, pair, repulsion. Okay, that is a test question. What in the world is VSEPR? That is how it's going to be worded. Not what in the world is VSEPR. No, that's a terrible question. What does the acronym VSEPR represent? It's probably how it's going to be worded. Okay? So here's the deal. VSEPR is a way to determine the three-dimensional shape of a molecule. That's the fancy name of what it is. Now, this last part right here, again, you've heard me say this over and over again. How do atoms want to be from each other? As far apart as possible. You should already know that. That's not a problem. You've already learned all that. Okay? Also, down there, if I were to ask you just the name of the shape of this molecule without you looking it up, what is that? Linear, bond angle, 180, hybridization, sp, very good, okay? This one, polar or non-polar? Be very careful. It's non-polar. Why? The F's are pulling in the equal strengths in opposite direction, okay? Now, here's the good part about it, Naja. It's only one part of the entire process. That's the good news. It's only one little small part of it. Yeah, each thing is worth the point. Okay, so let me go back and look at this. Guys, again, I like to teach different methods. I like to show you how to do it. I like to let you do it. I like to let you build it with your hands. I like to say it, and I like to let you read it. I'm trying to get all the learning styles. How many of you actually read and learn better than hearing, seeing it, or doing it? So, here's your reading. You can read this, okay? But if you read it in very skip form, the AB2 model is linear and it's 180 degrees. You already know that. AB3, 120, trigonal planar. AB4, tetrahedral, 109.5. So this is just summarizing everything that we've talked about in words. If you absorb things through words, how many of you absorb things through pictures? Here's your pictures. So I've given you words, now I've given you pictures. And you've all done this. So you've also done the kinesthetic aspect of it as well. So do me a favor. On this page, bonding domains. In the ABE model, what is the bonding domains? What letter would that be? These are your B's. And what are non-bonding domains? Those are your E's. And so if you write this right here, you've got A, B, 2. Do you have any E's? Nope, because it's 0. And what model would that be? Linear, okay? So we're good. What angle? 180 degrees. And so this is everything that you've learned so far thus in this chapter. Okay? None of this should be new to you at all. It all should be kind of easy to remember. All right, this next one. So, you good? Okay? You've got A, B, 3. Do you agree that this is AB3? What shape is this? Trigonal planar, bond angle, 120 degrees. Now, we've got a little error on this bottom one. My first question is, what is the ABE model with this last one? AB2E. Very good. Now, that says bent, but remember we don't call this one bent. What do we call this one? It's an A word. Angular. Very good. Do me a favor and please change that to angular. Angular. And the reason why is because there would be two bents if you left it like that, but they're two different molecules. Can I show you real quick the difference? How many lone pair are on that bottom one? 1. Let's go to the next slide. Look at the very bottom picture. How many lone pair on that one? 2. That's the difference. One has 1 lone pair, the other one has 2 lone pair. We don't want to call them the same name because they're two different things. And finally, the bond angle is less than 120 degrees. So here's the major concept I want you to get out of this. Okay? Lauren, look at those two pictures right here. What's the only difference between this picture and that picture? The only difference. This is an atom, and these blue things are electrons. Okay? So notice what happened. We swapped an atom for a pair of electrons, and what happened to the angle? It got smaller. So what does that tell you about these pair of electrons? they make the angle smaller. They push a little harder than an atom does. And so when we go to this next slide, you're going to be able to see the exact same thing happen again. Okay, so let's look at these pictures, and I'm going to do nothing but these pictures. What's the only difference between the top one, the middle one, and the bottom one? One has no E's, this one has one pair, and this one has what? Two pairs. So you already know this. What's the bond angle for tetrahedral? 109.5. All right, so we swap an atom for a lone pair. You've already told me the angle must get smaller. Does it for a trigonal pyramidal? What is it? 107. And then you swap another atom for another pair of electrons. Angle must get smaller. What is it for bent? 105. So you see specifically exactly how the model only changes by an atom, and it makes the angles get a little bit smaller because those pairs of electrons are a lot stronger. Okay, so again, this is your tetrahedral type of molecule, and you've drawn all these. Now, these next two slides are going to have some models that you are not required to know, but I don't want you to ever get to college or see it online or look at a worksheet and you freak out and say, hey, he didn't teach me everything. I'm okay with not teaching you all of these because look at these three. Seesaw, T-shaped, and linear. You don't have to know those. The only one you have to know on this one is the top one. But again, what's the only difference between the top one and the three bottom ones? You swap an atom for an E. That's the only difference. And what do you think happens to all these angles? They get less and less and less. Okay? And so that's kind of what's going on when you have that. So I just want to show you there are some more. And then the last one, which is the biggest molecule you can have, is the octahedral. And it's also got a square pyramidal and then a square planar. And you do not have to know the bottom ones. But again, just know that there are some optional. And what's the only difference between the top one and the bottom two? You swap an atom for a lone pair. That's the only difference in all of those. Real quick, the last thing I do want to write, what's the bond angle for octahedral? It is 90. 90 degrees, which means they're all at what kind of angles? Right angles. Okay. All right, so that's that one. Here's another picture if you like looking at other pictures. Did anybody get out of that? Did y'all get something out of that as we went? Hopefully, maybe, possibly. If you didn't, awesome. If you did, even better. I'm going to scroll through these real quick because I need to get to two things. I've seen that. I do want to ask you something real quick. If you see this on the test, which I'm forewarning you right now, you're going to see one very similar to this. Is there something special you have to do when you draw it? Brackets and the charge. Okay. What if it's a plus sign? Do you put a plus sign? Yeah. Okay. Do whatever the sign says. Again, and so when you look at the answer right here, that's not it. It is this one. Again, big old brackets. Draw the regular thing on the inside. Doesn't matter what's going on inside. That's normal. Just put it in brackets to put the charge on the outside. If it's positive or negative, just put whatever the correct sign is. Draw it normal and then just put brackets and a charge. That's the only difference. Oh, that's a good point. If it's negative, what do you do with the number? You add an electron. Yeah. Okay. Right here, Lauren, you see how it has the negative sign? Okay. If it's got one of these or a plus, you have to add that on the outside. Okay. But does that also affect the number of electrons you have? Because more than likely, when you add all these numbers up, you're probably going to get an odd number. Is that wrong? Yeah. Okay. If it's negative, add an electron. If it's positive, take one away. I know that's backwards, but okay. Next question. Here is another test question. That right there is a test question. When you think of a hybrid car, what does that mean? Okay, it's gas and electric. So do you agree it takes two things and it mixes them together to make a function? Okay, so hybridization. When you add the word ation or zation, what does that mean? The process of. So hybridization is the process of becoming a hybrid. Well, what does hybrid mean again? You just told me. You mix two things together. So here's what it is. A step further must be taken to explain how the orbitals of an atom are rearranged when the atoms form covalent bonds. And here, let me give you a visible example. And I really want to do this because it would be really fun. So pretend that Brett and I have two big, like, swimming rings around our bodies. You know what I'm talking about? Like a donut ring? Okay. So imagine if Brett and I tried to hug with those two rings on. Could we do it? Thanks, Brett. I appreciate it. Okay. Why couldn't we? The rings are kind of bouncing off of each other. Well, what are going around atoms constantly? Electrons. What do electrons do with each other? They repel. They bounce off each other. So pretend that those rings are kind of like electrons. So when you try to get close, what do those rings want to do from each other? They want to bounce. They want to push away from each other. But what happens if we could take those tubes and overlap them? Could we then get close enough to form a bond? Yes. Okay. So when you overlap those rings, when you overlap those orbitals, when you overlap the electrons, can they form bonds? Yes. And that's exactly what's going on here. So we use the model of hybridization, which is the mixing, the overlapping of two or more orbitals of similar energies to produce a covalent bond. Okay, so that's what has to happen, is you have to allow those orbitals to overlap or mix, because if they don't mix, they cannot bond. Let me go back real quick. So again, hybrid orbitals are orbitals of equal energies produced by a combination of two or more orbitals in the same atom. So we'll kind of go. So instead of it looking like a geometric shape, which you all hated geometry, right? Okay, it gives it more of this shape, which is what we've been drawing the entire time. So linear is not a line. It's really this balloon-looking shape, because everywhere there's a balloon can be some electrons, right? It's not just on the straight line. It actually can be in this specific area. And so that's something you'll kind of get more in tuned in with college if you ever take college chemistry, okay? All right, so the major topic of today, this word right here. So I want to break this word down for you again. We've done it once, but let's do it again. So here's the word. If I split this word right here, what does this prefix mean? Between. Very good. And molecular means molecule. And there are really two types of forces. What are there? All right, we'll go with that. Push, because that's shorter to right. But really, you can say attraction or repulsion, right? Push-pull, same concept. So what is an intermolecular force? And do not say push. It's a what? It's an attraction where? Between two molecules. So let me give you an example. What is that? And don't say water. It's an M word. It's a molecule. All right, so here's a very important question. What does this line represent? A bond. That's very important. Are intermolecular forces bonds? No. Reread what that says. An intermolecular force is a force where? Between molecules. What if I wanted to talk about in this molecule? That would be intra, right? We need to talk about between. So what do I need to draw to make it an intermolecular force? Another water. Very good. So let me draw, actually, let's do this. So, do I have two molecules? Those three little red dots are an attractive force between two water molecules. In other words, what can we call that thing? An IMF. Very good. So this is an IMF. Potentially. And let's get into that. When I write this word right here, do y'all know what the three states of matter are? Well, there's three major ones. So here's the deal. Jamila, do you agree that water, H2O, can be all three of these? Okay. What is the major difference between solid water and liquid water? Robert? Say that one more time. Molecules are closer together in a solid. Well, Robert, here's an important chemistry lesson of the day. What makes those molecules closer together? IMF. So what allows things to be really close? Intermolecular forces. So, Jamila, let me ask you this. If solids have lots of IMFs, how close are gas molecules? They're really far apart. So what do you think they have? Very, very few intermolecular forces. Okay? Yes, sir. Like a lot of IMFs? Yes. It's more than likely going to be a solid. Does that help? Okay? Yes, ma'am. We're going to get in there, I promise. I'm introducing the topic. Okay? All right. So if we go back and we look at this, I've got water stuck to water, right? What if I take a lot of waters and I stick a lot of waters together? What state of matter do you think it'll be? Solid or liquid? What if I take all those red dots and I erase them all? Probably is going to be a gas. More than likely it's going to be a gas molecule. And so that's how we have different states of matter. So I've got one other interesting point that I want to talk about. What happens in these two different reactions? Change colors. All right, so what? We need to talk about this. So, let me ask you something. What's specifically happening in the purple-pink reaction? Go ahead. That's true. Yes, that's the chemistry. In real life, what would you say is happening? It's melting. That's the perfect answer. Water is melting. Now, you told me it's melting, but Massimo, now tell me your chemistry answer. What's happening? Okay. Are you getting rid of IMFs or are you adding IMFs? You're getting rid of. You're losing them. Now, is the blue reaction completely and totally different? Yes. What's specifically happening to that water molecule? You're literally ripping it to shreds. So if I take this water solid and I put it to water liquid, is it still water? So basically, you're just erasing these red dots, right? But in this blue reaction, what else am I doing? I'm breaking bonds. I'm destroying these lines. And let me show you how you can look at the example. How many water molecules are there according to my balance formula? 2. Well, how many do I have drawn? I've got 2. When 2 water molecules are destroyed, how many hydrogen molecules can you make? You can make 2. And how many oxygen molecules can you make? You can make 1. Well, watch this. If I destroy both of these, do you agree that I got a hydrogen molecule there and a hydrogen molecule there? And then also, I've got an oxygen here and an oxygen here. So how many H2s do I have? 2 of them. How many O2s do I have? 1 of them. Does that make sense? So, in a change in a state of matter, which is a solid to a liquid, is it still water? Well, what happens when you change it chemically? It becomes something else. So, when you separate the intermolecular forces, is it still water? What happens when you break bonds? It's completely and totally different. So, when you separate IMFs, do you still have the same substance? Yes. That's the key that I'm trying to get you to see. And there's one other thing that I want to point out here. Oh, by the way, how could you do the blue part. Like, what could you do to make water turn into gases? Electrolysis. Stick electricity in it. It'll make it bubble. Okay? The bubbles are hydrogen and oxygen gas. So the only way to make that happen is electricity. All right. Now, real life. This is important. Okay? These two bullets are very important to you. Number one, how can you tell if two different things, of which two have stronger forces? The boiling point. Now, what in the world is the boiling point? And don't say the point at which. I know your answers for even saying them. It's the temperature at which what happens? Something boils. Now, what is boiling? Okay? So, when you've got liquid going into a gas. Now, if you don't want something to boil, do you want it to have really strong forces or really weak forces? Really, really strong, right? You're going to hold it together. So the boiling point is a good measure of the forces between molecules. The higher the boiling point, the stronger the force. I'm giving you another test question. That is a test question. The higher the boiling point, the stronger the forces. What does that mean? The force be with you, right? The stronger it is, the harder it is to get apart. Okay? Is it easier to break a paper chain or a steel chain? Steel, right? It's stronger. You have stronger forces there. The second bullet. Intermolecular forces vary in strength but are generally weaker than bonds. Okay? We just talked about this example. So, if I want to erase the 3 red dots or the black line, which one would be harder? The bond or the IMF? Which one's harder to do? The bond is harder to break. Okay, the bond is much harder to break. All right, so let's talk about, we're going to skip that. All right, so let me go back to this and let me just give you another example. Okay? So let's look at these two. So here's my question. Is one of these more electronegative than the other? Yes. Which one? Fluorine. So if I want to share an electron, this is going to happen, right? Yes. Now, remember these things? One side is partially something and one side is partially another thing. Which one is the fluorine? Why is it negative? Because it's gaining the electrons. Do you agree that this thing is a molecule? Yes. Can I stick another HF onto this thing? Can two molecules stick together? Yeah. So let me ask you something. This is a very important question. Do you agree that the hydrogen end is positive and the fluorine end is negative? Of the other molecule, which end would the fluorine want to attach to on the other one? Why the hydrogen end? What do opposites do? Attract. Very good. So here's what we got going on. So we got H bonded another HF. We've got this exact same thing going on. Okay? So again, we've got partially positive, partially negative. And here we have an IMF. Now, does this make sense? Okay? Two things are stuck together. I told you a minute ago that how many possible answer choices are there for an intermolecular force? There are 3. So here are the 3. The first one, does anybody remember one? Number 2. And finally, number 3. So, on Friday, these are your 3 possible answer choices for the very last question. I'm fixing to explain that. Okay. So, as what we're fixing to talk about, you've got to remember that these are your only possible answer choices. Okay? So, hydrogen bond, dipole-dipole, or LDF. Which IMF is within the molecule? Okay, I'm fixing to explain it to you. I'm telling you these are your only possible answer choices. So when we look at this, this tells me that the strongest intermolecular force exists between what? And this is important. 2 what? Polar molecules. And this is the next key word. Because of their uneven charge distribution, polar molecules have what? Dipoles. Now let me think about something. What does di mean? What does pole mean? What's the two poles? Positive and negative. So this is interesting. You told me just a few minutes ago that this HF is polar or nonpolar. Polar. Does it have two poles? So what can we call this? This is the dipole. Well, here's the next interesting thing. This H and this F, are they polar? Does it have two poles? What is it? A dipole. So if you've got two different dipoles, can you stick them together? Which intermolecular force would it be? Well, that's interesting. This is a dipole-dipole. Okay? So how do you know if it's a dipole-dipole? If it's two polar molecules. That's how you know. Because one is a dipole and the other one's a dipole. So it's a dipole-dipole intermolecular force. Okay? All right. So that's the dipole-dipole. Remember, how many answer choices do you have? 3. We've covered number 2. Now let's talk about number 1. Again, a dipole is created by equal opposite charges, blah, blah, blah. We're going to skip that. We're going to skip this. We're going to skip that. Oh, real quick, I do want to point this out. Real quick, let's look at the very last bullet. The boiling point of iodine and chlorine is 97, but the boiling point of bromine and bromine is 59. Why do you think that iodine and chlorine, that molecule, has a higher boiling point than BrBr? Say it again. It's polar, and polar are stronger or weaker than nonpolar. They're stronger. That's why it's higher. Very good. Okay, so we're going to skip this. We're going to get to this part right here. Hang on. I don't want to run short on time. Okay, so this is the slide. So some hydrogen-containing compounds. I'm going to stop right there. What IMF you think we're getting into? Hydrogen bonds. So this is where you're going to have to know about hydrogen bonds. Have unusually what? High. So the higher the boiling point, the stronger or weaker it is. The stronger it is. This is explained by a particularly strong type of dipole-dipole force. So here's what you need to understand. Hydrogen bonding is a type of what? Dipole-dipole. It's so special, it got its own name. Like it's completely and totally separate because it's so strong. And so here's what you have to know. A hydrogen bond must have at least what? A hydrogen, but it must also have some bond. Okay, what in the world do I mean by bond? It's got to be between a hydrogen and a fluorine, a hydrogen and an oxygen, or a hydrogen and a nitrogen. So if it's a hydrogen bond, it's a very polar molecule that must have hydrogen and some fun. Not any fun, because uranium wouldn't work here. Yes, sir. Okay, hold that. I'm going to get there. I promise I'll get there. Okay? So, my world kind of got shattered a few weeks ago because I read an article that they have now found hydrogen bonding and phosphorus as well. So now it's not only... So again, now let's go back and let's look at this example. You told me a minute ago that this was polar, so it's a dipole. You told me that this HF was polar, so it's a dipole. You told me this was a dipole-dipole. But could this possibly be hydrogen bonding? Does it have a hydrogen? Is it having any fun? It dang sure is. So this one is not just a dipole-dipole, it's also a what? Hydrogen bond. Let's go back and let's look at another example. Let's look at water. These two things are stuck together. Is water polar or nonpolar? It's polar. Does it have a hydrogen? Is it having any fun? So this IMF is specifically what? Hydrogen bond. Well, let me give you one more. What happens when you take the H and you swap it with an I? Now, my first question is, are both of these things polar? Yes, they are polar. Does it have a hydrogen? But is it having any fun? Nope. So this was not hydrogen. This is what? Dipole-dipole. You with me? One last example. What if you've got S swapped for O? So you got hydrogen, but is it having any fun? So this is no longer hydrogen bonding. It's what? Dipole, dipole. So do you see the differences? And here's the very last example. What's the last one we haven't talked about yet? The LDF, which stands for London Dispersion Force. Okay? All right, so real quick, I know that this kind of looks like Mickey Mouse, right? The red is your oxygen, the white is the hydrogen, and notice how they're connected together. It's by dots, so these are forces, right? Also, how many of you liked DNA when y'all did it in biology? Enjoyed it? What happens to DNA all the time in your body? It's going through replication. Do you remember it's got to unzip and it's got to zip back up, right? Well, if you have to unzip it, does it need to be a really weak force or really strong force? Really weak. So think about it. The bonds between the nucleotides in DNA, remember A with T, G with C? They're held together by hydrogen bonds. So let's go in and let's look at the picture right here. Don't scream at me. Hang on. This slide talks and I hate it. Notice what you have between A and T. This is something you probably never noticed before. But these are hydrogen bonds that are holding these things together. Well, what happens when you go through mitosis or replication? You got to unzip it. It replicates itself and does what? Zips right back up. So these are strong, but they're weak enough that they can zip and unzip all the time. And so that's why hydrogen bonds are between these two things. So that's an additional set of knowledge that was there. You just didn't know exactly what it was. Okay? And the last thing, the London Dispersion Force. The thing that you need to know about London Dispersion Forces is that it's going to be between... No, hang on. Where is it? I'm looking for a word. There we go. This is it right here. So this is the whole key. Let me get a color that works. Of a LDF. So dipole, and hydrogen bonds are between what two types of molecules? Polar molecules. Okay. What is a LDF between? Two non-polar molecules. And let me give you a real life example. This is how I think about it. I pretend that, well, here, let's look at this. It's actually better if you see it drawn. What happens if you have iodine and iodine? Which I is stronger than the other? Neither one of them. So do you agree that this kind of happens? Now, again, it would be a lot more perfect if I did it. Iodine has 53 electrons here and 53 electrons here for a total of how many? 106. Would you agree or disagree that every moment of every split second of every single day that it's always 53 and 53? Agree or disagree? Disagree with that statement. Because what are electrons constantly doing? They're constantly moving. So for a split momentary second, could you have like 70 here and like 36 here? Yeah, and in the very next second, what could happen? You could have 26 here and 80 here. So constantly, is it going to be imbalanced? Okay, so for the blue color, do you agree that this side is going to be partially negative and this side is going to be partially positive? Well, what happens in the very next second? What happens to those poles? They swap. So this side you've got partially positive and this side you've got partially negative. Well, what happens if it's got another molecule flying by? What happens if at the same time they're flying by each other, they're opposite charges? What can they do? They can attract. So here's how I like to think of an LDF. It's a high five. Okay? They high five each other, they're stuck together for a momentary second, and then they keep right on moving along. Okay? But that's what an LDF is. It's because that momentary second, remember how fast are electrons moving? The speed of light. Right? And so it's only going to happen for a split second. That's why I'd say it's like a high five. So it's just enough time for them to stick and keep moving. Okay? And so that's an LDF. Any questions? Yes, only between two non-polar. So the last little thing. Guys, when you start answering those questions, look at the last two things. Molecule polarity. If you write the word non-polar, what's the very next thing you write? LDF. You don't even have to think. If you write non-polar, write LDF. If you write polar, you got to think just a second. What's the first thing you look for? The hydrogen. If it does, it might be hydrogen bonding, but it's got to have what, Ryan? It's got to have some FONT. Okay, I won't do the FOMP. Nope, we're not getting there yet. That hasn't been proven statistically, but they think they've got it. So again, the last two aren't too bad.